Today we are going to discuss a very important concept which is integral form of Bessel function. So in this regard, first of all, we will see how we can define the integral form of Bessel function, that is Jn of x. In fact, in previous lecture, you have already studied the generating function for the Bessel function Jn of x, and you know it is defined in this way: e raised to the power x over 2 t minus 1 over t equal to summation n minus infinity to plus infinity tn Jn of x. Now, if we expand the RHS of this equation, then what will be our result? You can see easily. Let us put the value of the different terms after substituting the limits. In fact, this after expansion we will get actually j naught of x plus t j1 of x plus t square j2 of x plus t cube j3 of x plus so on. And now this has been actually obtained by putting n equal to 0, n equal to 1, n equal to 2 and so on. Now when we will substitute the negative value of the limits, that is negative value of n, then what will be our result? You can see if we start from n equal to minus 1, then when n is equal to minus 1, then term will be t minus 1 j minus 1 of x plus t raised to the power minus 2 j minus 2 of x plus t raised to the power minus 3 j minus 3 of x and so on up to minus infinity. This term will be in this series. Now we know j minus n of x is equal to what? It is simply minus 1 raised to the power n jn of x. So on the basis of this formula, you can evaluate the value of j minus 1 of x. So when we will find j minus 1 of x, you can see here n is equal to 1. So let us substitute minus 1 raised to the power 1 j1 of x. And you know minus 1 raised to the power 1 will be what? That will be simply minus 1. So this is minus j1 of x. Similarly, j minus 2 of x will be what? You can write this is minus 1 raised to the power 2 j2 of x. But you know minus 1 square is simply equal to plus 1. So this will be simply j2 of x. Similarly, j minus 3 of x, this will be equal to minus 1 raised to the power 3 j3 of x. And as you know, minus 1 raised to the power 3 will be simply minus 1. So that will be minus j3 of x. And in similar manner, you can evaluate the other Bessel function of this type j minus n of x. Now we will substitute all these values in the above equation which I have defined here. So now let us substitute this. You can see e raised to the power x over 2 t minus 1 by 2. All the terms in the series containing positive value of n, that will remain same. So I have repeated it. This is j naught of x t j1 of x plus t square j2 of x plus t cube j3 of x and so on. And when we will substitute the values which we have defined here for the j minus n of x, then you can see this will be simply minus t raised to the power minus 1 j1 of x plus t raised to the power minus 2 j2 of x minus t minus raised to the power minus 3 j3 of x and so on. Now we will combine all those terms containing the same jn of x. So you can see j naught of x is an in fact independent term. There is no other term containing j naught of x. So j naught of x remains at each. Now you can see there are two terms in which j1 of x is contained. First one is t j1 of x and second one is minus t raised to the power minus 1 j1 of x. So if we will take j1 of x as a common factor, the remaining term will be what? That will be simply t minus t raised to the power minus 1, and t raised to the power minus 1 can be written as 1 over t. So the second term is t minus 1 over t j1 of x. Similarly, you can see there are two terms in this series containing j2 of x. So again we will take j2 of x as a common factor, and the remaining term will be t square plus t raised to the power minus 2, and t raised to the power minus 2 can be written as 1 over t square. So this is t square plus 1 over t square j2 of x. And similarly we can take j3 of x as a common factor. So you can see here that this term is this like this, and in this way we can also associate other terms containing j4 of x, j5 of x, j6 of x, and so on as a common factor. Now to simplify this RHS of equation 1, let us put let t equal to e to the power I theta. Let us put, and you know t to the power I theta, this is equal to cos theta plus I sin theta. You know it. And now we will use de Moivre's theorem here to simplify the RHS of equation 1. So you can say by de Moivre's theorem, de Moivre's theorem, you know from de Moivre's theorem that t raised to the power n, this will be equal to e raised to the power I n theta, and this may be equivalently written as cos n theta, see here, cos n theta plus I sin n theta. And in similar manner you can write t raised to the power minus n, or you can say that this is 1 over t raised to the power n. This will be equal to e raised to the power minus I n theta, and this will be cos minus n theta plus I sin minus n theta. But you know cos minus n theta is simply equal to cos n theta, but sin minus n theta, this is minus sin n theta. So you can write this as minus I sin n theta. Now as in equation 1, you can see there are terms containing t minus 1 over t, t cube minus 1 over t cube, and similarly other terms. And at the same time there are also terms like t square plus 1 over t square, t4 plus 1 over t4. So from these two equations, that is for the values of t raised to the power n and 1 over t raised to the power n, we can find all those terms from here. So you can see if we want to calculate t raised to the power n plus 1 over t raised to the power n, then you can see what will be your term. As I have defined these here, you can see. So this will be simply equal to, you can see, cos n theta plus I sine n theta and plus, as 1 over t is what? This is cos n theta minus I sine n theta. You can see I sine n theta. You can see I sine n theta will cancel out here. You can see, yes, and the term will be cos 2 cos n theta. And similarly, when we calculate t raised to the power n minus 1 over t raised to the power n, then this will be cos n theta plus I sine n theta and minus cos n theta and plus I sine n theta. You can see here this cos n theta will cancel out and our result is 2I sine n theta. 2I sine n theta. Now we have evaluated the values of t raised to the power n plus 1 over t raised to the power n and also t raised to the power n minus 1 over t raised to the power n. Now we will substitute all these values in the RHS of equation 1. So you can see substituting these values in equation 1, we get what you will get. You can see easily our equation 1 is e raised to the power x over t times t minus 1 over t. So you can see here this will be e raised to the power x over t and t minus 1 over t. So you can see from here t minus 1 over t. It means we have to take n equal to 1 in this expression. So when n is 1, then you can see this term will be equal to 2I sine theta. N is 1 here. So this is simply e raised to the power x over 2I sine theta. So you can see this 2 and this 2 will cancel out and this is equal to e raised to the power ix sine theta. And now use these results in RHS of the equation 1. So here you can see there is j naught of x. So we will write simply j naught of x and plus the second term is what? The second term is t minus 1 over t j1 of x. So again we will put the value of t minus 1 over t from here, taking n equal to 1, and you can see easily that this will be 2I sine theta j1 of x and plus, then you can see your second term is t square plus 1 over t square j2 of x. So t square plus 1 over t square, we will find it from here taking the value of n equal to 2. So when we will take n equal to 2, then this will be t square plus 1 over t square and that will be equal to 2 cos 2 theta, because you can see here there is n and n is now 2. So this will be 2 cos 2 theta times j2 of x and plus, again see the next term, this is t cube minus 1 over t cube j3 of x, and to get the value of t cube minus 1 over t cube, we will put here n equal to 3. So when n equal to 3, then this will be t cube minus 1 over t cube, and that will be equal to 2i sine 3 theta, because n is here 3. So you can see this will be plus 2i sine 3 theta j3 of x, and plus so on. In this way we can write any term in this series. Now you can see this e raised to the power ix sine theta is equal to this much. So now we arrange this term in a particular manner containing all the real terms jointly and the all imaginary terms jointly. But first of all, see, you can write e raised to the power ix sine theta. You know, this can be written as cos x sine theta plus I sine x sine theta. You can write it x sine theta. Now one equation is here. Let us say this is equation 2 and this is equation 3. Since LHS of these two equations you can see are same, it is e raised to the power ix sine theta. So we can compare these two equations, and you know, if two complexes are same, then definitely the real part of the first complex is equal to imaginary part of the second complex. So now we will equate the real and imaginary part of e raised to the power ix sine theta from equation 2 and from equation 3. So now let us equate it. So you can see equating real and imaginary parts in 2 and 3. In 2 and 3 we get what will be our result. You can easily recognize it. You can see in LHS actually the real term is what? A real term is cos x sine theta. So we will write cos x sine theta, and in RHS you can see j naught of x is real, 2 cos 2 theta j2 of x is real. Similarly, in fact 2 cos 4 theta j2 of 4x will be also real. So the term which is real in RHS is what? You can see easily, this is j naught of x plus, as in all real terms this 2 will be just as a common factor. So you can write 2 as a common factor, and then there will be cos 2 theta j2 of x, similarly cos 4 theta j4 of x, and so on. You can see, and so on. So let us say this is equation 4. Now again we will equate the imaginary parts of the two sides. So you can see the imaginary part of e raised to the power ix sine theta is what? This is simply sine x sine theta. So we will write here sine x sine theta, and that will be equal to Now see the RHS. Here is a term 2I sine theta j1 of x. Another term is 2I sine 3 theta j3 of x. So these are actually imaginary terms in RHS. So we will combine all these imaginary terms here, and you can again see that 2 appears as a common factor, and the integer which is multiplied to theta are actually odd integers, so that will be 1, 3, 5 and so on. So this will be actually equal to 2 times of sine theta j1 of x plus sine 3 theta j3 of x, and plus so on. You can see, let us say this is equation 5. Actually the equation or the series which are actually defined in equation 4 and 5 are known as Jacobi series. This is a very important series in mathematical physics. So the series defined in 4 and 5 are known as Jacobi series. Jacobi series. Now we will follow a particular step to evaluate the integral of the LHS of equation 4 and equation 5. In fact, for this we multiply both sides of this equation 4 by cos n theta, and then we will integrate this with respect to theta between the limits 0 and pi. Then you will actually found that when n is odd, all terms on the RHS will vanish, but when n will be even, then all terms on the RHS except one containing cos n theta will vanish. So we can write the general form of this equation in this manner. So you can say multiplying both sides of equation 4 by cos n theta and integrating with respect to theta between the limits 0 and pi, we get, you can write these integrals as integral 0 to pi cos x sine theta times cos n theta d theta, because we have multiplied it by cos n theta. And then as I have told you that when you will do it, then when n will be odd, all terms on the RHS will vanish, and if n is even, then only one term will remain non-zero, and that term will contain actually cos n theta, and all other terms will vanish. You can check it. So we can write this integral in this manner. This is equal to 0 when n is odd. You can check it. And this will be equal to pi times jn of x when n is even. You can check it and say this is equation 6. In similar manner, we will now multiply the equation number 5. See here, equation number 5. This equation 5, both sides by sine n theta, and then we will integrate this result with respect to theta between the same limit, that is 0 and pi, and then you will get actually just the reverse result. That is, when n will be even, then all terms in RHS will vanish, and when n will be in fact odd, then only one term containing sine n theta will remain non-zero. So you can see multiplying equation 5, both sides by sine n theta, and integrating between the limits 0 and pi, we get, in this condition our result will be integral 0 to pi sine x sine theta times sine n theta d theta, and that will be equal to pi times jn of x when n is odd, and this will be equal to 0 when n is even. Say this is equation 7. So you can check these results in RHS after doing the integration. Now we will simply add these two equations, 6 and 7. You can see in LHS there will be sum of these two integrals. For this integral and this integral will be added, and in RHS you can see when n will be odd, then in RHS there will be 0 plus pi gn of x, that is pi gn of x, and when n will be even, then the sum in RHS will be pi gn of x plus 0. It means when n is either even or odd, the result will be same, and that will be simply equal to pi gn of x. So you can easily say that after adding we get, when you will add these two equations, you can see this is integral 0 to pi cos x sine theta cos n theta plus sine x sine theta times sine n theta d theta, and that is simply equal to pi jn of x, and in fact this result will be valid when n is either even or odd in both conditions. So you may mention this condition that when n is odd or even, in both conditions we will get this result. So actually this is the integral form of Bessel equation, Bessel function, and you can let us say simplify this result one step ahead. Let us see here. You can say that from this result that this Jn of x will be what? Jn of x will be what? You can see Jn of x will be equal to 1 over pi integral 0 to pi. Now see here, you know the formula cos a minus b is what? You know this is cos a into cos b plus sin a into sin b. You know it. Cos a minus b is written as cos a into cos b plus sin a into sin b. So from this formula we can simplify this result, that cos x sin theta cos n theta plus sin x sin theta sin n theta. So you can see n theta is at the place of a or b and x sin theta is at the place of a or b. So using this formula of trigonometry, you can write that this is equal to cos n theta minus x sin theta d theta. So actually this is the integral form for the Bessel function Jn of x, and from this result you can write the value of Jn of x for any integral value of n. So this result is valid for all integral values of x. So you can obtain its particular values by putting n equal to 0, 1, 2, 3 and so on. So if in particular we find the value of j0 of x, so you can see if n equal to 0, then what will be our result? You can see this will be j0 of x equal to 1 over pi integral 0 to pi and cos n theta, n is 0, so this will be 0, this is 0, sorry, this is 0, this is 0, and minus x sin theta. So this will be minus x sin theta d theta. But you know cos minus theta equal to cos theta, so you can write it, this is simply 1 over pi integral 0 to pi cos x sin theta d theta. So evaluating this particular integral, you can find the value of j0 of x, or you can say this is the integral form of the equation defining the value of j0 of x. So here in equation A we have obtained the integral form of Bessel function Jn of x, and from this you can see we can obtain any particular value of Jn of x simply taking the integral value of not x but integral value of n, integral value of n. So this is all about the integral form of Bessel function Jn of x. Now in next lecture we will see some of the important problems based on this concept.